Half-lives. Nuclear stability and decay. The whole reason atoms decay is because they're unstable. So they're going to keep decaying until they finally hit a stable nuclear state. Elements with an atomic number greater than 83 are radioactive. Elements with atomic numbers less than 20 want to have equal protons and neutrons. Elements with higher atomic numbers need more neutrons to protons in order to be stable. There are some exceptions to this, but for the most part, the elements below 20 have equal protons and neutrons. If you look at this band of stability graph, you can see protons on the x-axis and neutrons on the y. And if you find atomic number 20, notice that an equal 1-to-1 neutron-proton ratio is in that band of stability. But as the atomic number increases, you need more neutrons to be in this band. So what type of decay depends on how many neutrons to protons it has. Heavier elements usually undergo alpha decay, while lighter elements will undergo beta and positron emissions. If the mass of the isotope is greater than the average mass, which is located on the periodic table, then most likely the element will undergo beta decay. If the mass is less than the average mass, which is on the periodic table, then it will undergo positron emission. So pause the iPod and figure out which type of decay you think these isotopes will undergo. Since carbon-14 is greater than carbon's average mass of 12, it should undergo beta decay. Since carbon-10 is less than the average mass of carbon, which is 12, it would undergo positron emission. And since radon-222 is heavy, it would undergo alpha decay, most likely. So all isotopes have a rate of decay. This rate is called the half-life. Make sure you know the definition of the half-life. A half-life is the time required for 1/2 of the material to decay. Half-lives can be very short, as in fractions of seconds, or can be very long, as in billions of years. Make sure you know how scientists use half-lives. Make sure you read the paragraphs in your note packet that correspond to this, which would be carbon dating and for medicines. Here's a type of problem that you can see. It says, how long is 3 half-lives? The first thing you need to know is in the problem it says the half-life of 10 minutes. So because of that, we know that 1 half-life must be 10 minutes. And if 1 half-life is 10 minutes, then 3 half-lives must be 30 minutes. When you're trying to find out how much will be present at the end of 3 half-lives, or really any half-life problem, you need to set up a chart with half-life, time, and amount. The first column for half-life should always be 0, as should it for time, because no time has gone by, and so no half-lives have gone by. And your starting amount, which in this case is 2 grams. After 1 half-life, 10 minutes has gone by, because 1 half-life is 10 minutes. And our amount, according to the definition, should go down by 1/2, so we have 1 gram left. After 2 half-lives, 20 minutes has gone by, and we have 0.5 undecayed. And after 3 half-lives, 30 minutes have gone by, and we have 0.25 grams left undecayed. On this problem, it says a sample of radioactive element decays to 25% in 12 years, and we're trying to find the half-life. So half-life is 0 and time is 0. And because we're dealing with percent, you should always start with 100%. Pause the video and try to figure out the rest of this one on your own. After one half-life, we don't know the time yet. So scratch that. But we do know that the amount should go down by 1/2, so 50%. After 2 half-lives, we should have 25%. And it says that when we have 25%, it's been 12 years. So now we can find our half-life time by doing 12 divided by 2, giving us 6. So 6 is how long one half-life is. So we divided 12 divided by 2 because it's time over number of half-lives. And that should be number of half-lives. So wait for the correct formula. And you need to write this formula on your paper. So anytime you're looking for how long one half-life is, you're going to do time elapsed over number of half-lives is equal to half-life time. And so that's how we got 6 years. So you don't always divide by 2, just in this case because that was how many half-lives had passed. Go ahead and pause the video and try this one on your own. So we started with 0 half-lives, 0 time, but we're trying to find out how much needs to be ordered. So that's our starting amount. So we don't know that. We do know after one half-life, 3 days have gone by because that's how long one half-life is. So filling in your table, we're going to keep going until we hit 15 days. Because at 15 days, we know that we need 1 gram for the study. Because amount always decreases by half, we can multiply by 2 and go up the chart, and so we need 32 grams. I'm going to pause the video and try this one on your own. So 0 half-lives, 0 time, and we're starting with 10 grams. One half-life is 70 years, and so 5 grams, and we're going to keep going until we hit 1.25 grams. And it just wants to know how many half-lives had passed. So our answer is 3. So in this case, we didn't really need that middle column. And sometimes you can only have 2 columns because they don't give you enough information to fill out all 3. But start with a 3 and then figure out what you know and where you can put more info. Pause the video and try this one on your own. So 0 half-lives, 0 time, and we're starting with 80 grams. And we're going to keep going. We don't know how long one half-life is though because it doesn't say. So we're just going to keep adding our half-lives and decreasing our amount by 2 until we reach 10 grams. When that happens, we know we're at 24 days. It wants to know how much it remains unchanged after 8 days, so we need to find out how long one half-life is. So 24 divided by 3 gives us 8. So notice, after 8 days, 40 grams is unreacted. So that's our answer. Fission is the process of splitting a larger atom into smaller atoms, often producing gamma rays and free neutrons, as well as lots of energy due to them being extremely exothermic. You're going to see fission reactions in nuclear power plants, as well as atomic bombs. So a neutron hits a nucleus, so it induces fission. It breaks it into two equally sized atoms, are roughly equal, and more neutrons. Those neutrons then go off and can break other atoms up. And so this is a chain reaction in which the products start the next reaction. This can grow exponentially if uncontrolled. So in a nuclear power plant, they have to control this by absorbing some of those neutrons. And cadmium usually does that, cadmium rods. Fusion is the process in which multiple atomic nuclei join together to form a heavier nucleus. And fusion is going to occur on the sun. It takes a lot of heat to start this reaction. So you have deuterium and tritium going together to make helium and a free neutron on the sun, as well as lots and lots of energy. The benefit of fusion is there's no radiation given off. So read those two paragraphs in your note packet.